So good morning, welcome to the Floating Offshore Wind track. This is the first session of two. We'll take questions from Slido, both in person and the virtual attendees. Okay, so I'm Monica Marr, offshore wind specialist with Lyndall Reed, supporting the U.S. Department of Energy's Wind Energies Technologies Office. And welcome to the Floating Offshore Wind Deep Dive. So Department of Energy has a series of energy Earth shots, which are the moonshot of our generation, and they represent goals far beyond the business as usual. So achieving the long-term shot goals is a all-hands-on-deck approach that will require additional resources for federal and state governments, industry, and researchers. The United States is going to need a diversity of clean energy resources to have a clean energy sector by 2035 and achieve a net zero economy by 2050. So last year in September, the floating offshore wind shot was announced as one of these. So this is chosen because offshore wind is especially well suited to provide clean energy to densely populated coastal regions that have a large demand and may have limited space for land-based clean energy and transmission. And then additionally for the US, about 2/3 of the offshore wind resource is over waters too deep for fixed foundations. So the shot goal aims for a 70% or more reduction of costs down to $45 per megawatt hour by 2035. So achieving this would drive US leadership for both design, manufacturing, and deployment. And along with the shot announcement, Department of Interior also announced a 15 gigawatt deployment target that would also, with the goal of protecting biodiversity and promoting ocean co-use. So to rapidly move the United States from just technology demonstration towards commercial scale deployment is going to need an all-of-government approach. And the floating offshore wind shot is a partnership between Department of Energy, Department of Interior's BOEM, Department of Commerce's NOAA, Department of Transportation, as well as the Federal Permitting Improvement Steering Council. So to address industry challenges and accelerate floating offshore wind, the shot has 5 pillars. So developing cost-effective floating offshore wind technologies to harness the power above deep US waters, promoting energy justice with environmentally sustainable and just deployment to ensure that marine wildlife coexists and that other ocean space users can thrive alongside floating offshore wind, and to benefit local economies and underserved communities to reduce the climate and health and environmental impacts of the US energy sector, as well as supporting supply chain development, including port construction, and scaling up domestic manufacturing capacity, especially for turbine platforms and components, while considering the local workforce, materials, and infrastructure needs. Designing transmission networks and configurations to connect the best wind sources to the load centers, and advancing research in future transmission technologies, including HVDC, to enable the long-distance transmission far from shore. And finally, fostering economy-wide decarbonization by advancing floating offshore wind energy storage and clean fuel production. So the shot is intended to be an ambitious call to action as part of a wider effort to decarbonize the grid. R&D contributions towards the cost reduction can be made across several areas, including large turbines with higher generating capacity while maintaining a high reliability of operations, serial manufacturing and design for production, systems engineering and operation, and increasing operational reliability through improved maintenance capabilities and lifetime extension practices. So now we'll start the floating offshore wind deep dive. This is the first of 2 panels. So this panel focuses on anchoring, station keeping, and platform stability. We'll have Zach Miller from Triton Anchor presenting on their innovative anchoring system for floating offshore wind. Spencer Hallowell from University of Maine presenting on design and certification of taut synthetic moorings for floating offshore wind. And Biao Feng from GE presenting on the dual functional tuned inerter damper for enhanced semi-sub offshore wind turbines. So again, you can put questions in the Slido app, and we'll take them after the 3 presentations.
All right. Hello, everybody. My name is Zach Miller. I'm the Chief Technology Officer at Triton Anchor. Just a little bit about us. So we are a spinoff of a company called Triton Systems. Triton Systems is a technology developer of a variety of different markets, creating new ideas for the country. And so now we've officially are a separate company with our own mission and goal. So our mission is basically provide cost-effective anchoring systems for offshore renewable energy, specifically focused on floating wind. And we're right outside of Boston, Massachusetts. So we've had a lot of partners and collaborators and funding sources over the years. The ones that are circled are the ones specific for this program that we ran through through now RDC. So University of Massachusetts Amherst was involved, University of Rhode Island, and then American Bureau of Shipping were the ones involved in this specific test. All the other ones, US DOE has funded us several different rounds for our technology, along with Massachusetts Clean Energy Center and California Energy Commission. So here's our team. I think we've added 5, 6 people in the last 4 or 5 months. So we're growing pretty fast here with a goal of deploying 4 anchors at the end of 2024 off the coast of Oregon for one of our clients. Range of engineers, business development, sales, marketing, executives round out the team. So I guess I'll kind of start with why we're going after this, what we're doing. So the current challenges with the anchors that are out there today is they're too expensive. So as we want to lower the cost of energy from the shot, we're looking for cheaper anchors. The infrastructure that's around and to do these anchors, the current ones out there, they just can't scale to meet the need, the quantities, and the timelines that we need to deploy them. They potentially destroy habitats. And then noise pollution related installation and the potential failures. So kind of what that means if this is the current solutions to date is potentially like wave energy, so it's slightly different than wind, just can't be affordable, so the costs are even harder there. So there's technologies that just can't be deployed. Wind farms potentially can't be done on schedule, so there's a lot of things, and potentially anchors. If you have 3 or 4 anchors per turbine, those quantities are very, very high. So even manufacturing 1 turbine per week, now you're going to manufacture 3 to 4 anchors per week, right? So it's just a lot of quantities over and over again. And then just more vessels, more sound mitigation technologies that you need to not pollute the marine environment. So we created a solution about 7 years ago using helical piles. Helical piles are used for land-based infrastructure. This building might have helical piles on it, bridges, guide wires, things like that. So what we're doing is we're using that same size that they use for land-based infrastructure. Instead of scaling up the helical pile size, we use that size and a quantity. We use that quantity, we tightly cluster them together, and then we kind of bound it by an exterior caisson skirt. The skirt's more of a short and stubby to provide some resistance laterally, and provides us a kind of a solid foundation for the whole anchoring system. Ultimately, our system can be done for any type of platform. So that's a semi-submersible spar, tension leg system. We can do any type of loading direction, vertical loads, horizontal loads, multi-directional loads, shared anchors, things like that. So the whole focus, the main focus of the Now RDC program was going through the American Bureau of Shipping new technology qualification process. So that process for ABS is a 5-stage process. 4 of the 5 stages we did under the Now RDC program. So we completed all those stages. with ABS, reviewing and witnessing engineering calculations, risk assessments, manufacturing plans, test results, numerical analysis, variety of different engineering and other items. And then we're currently performing the last stage in 2024 to be a fully qualified new anchoring system. So one of the biggest kind of tasking that was associated with those first 4 stages was basically site investigation, designing, manufacturing, installing, and testing anchors for basically qualification of our analysis for larger commercial scale anchors. Since we can't really we can't test full commercial scale anchors, we have to basically do smaller anchors and then model them and then use those analysis to scale up. So these are the 2 anchors that we built and installed. We basically tried to go as big as we could given kind of standard US DOT restrictions and then also cost effective to pull out because we pulled these anchors to failure to get a lot of variety of testing. So you can see the 2, we did one that was more vertically, was going to be tested vertically, and then we did one that was more tested horizontal. And then the anchor weight's about less than 7,000 pounds. We wanted to do the same number of piles. We wanted to try to do as many piles as we could because that's kind of the one aspect of our design is tightly clustering helical piles. And then we went to the same depth to not have too many different factors. Yeah, so basically what we did is, like I said, we went out, we manufactured these anchors. We then brought them to the test sites. The University of Rhode Island has a research farm that's kind of in a low basin, so the water table is pretty high. So it kind of naturally mimics wet soils. We then built an installation tool. So this is a proprietary installation tool that basically installs our anchoring system. You can kind of see in these photos where we're taking the anchors off of the trailer. And then the other photo shows the installation tool on top of the anchor about to be installed. So this is kind of the installation process in picture format. As you can imagine, basically the tool starts on top of the anchor, and then we screw the helical piles in, and then we pull the case on it at the same time. We then tested out an additional method of basically jetting in the skirt. To help us we measured the capacity necessary to install it without the jetting, with the jetting, to see what the forces were. And then ultimately, the far right picture is basically the fully installed anchor. So we did that twice, and then we basically did load testing. So the picture on your left is the test for the pure vertical loading. Just given the constraints of what was available to us, given a reasonable cost and budget, we basically just did a pure vertical test and then a pure horizontal test. So a big load beam across the anchors, some cribbing so it reacts against the ground, and then a load cell hydraulic jack attaches to the center of the anchor, and we pull up. And then the one on the right-hand side is the pure horizontal load, so we attach the 2 anchors together, so it was actually cheaper to use our failed anchor, well, the one that we just did a vertical test on as the reaction to the other one that we're testing for the horizontal. That was actually cheaper than them installing their own foundation to test against. So we were like, well, why not, right? And then basically 2 jacks on either side, and then a big wire rope basically connecting them to provide the load. So basically what we're measuring is we're measuring displacement versus load. So the 2 dotted lines, we measured basically the jack load, so just off of like effective area and hydraulic pressure. And then we had a load cell in line, so we had 2 measurement basically basis. And then the solid line is our analysis of what we expected it to be. The vertical dotted line is where we define failure for our anchoring system. So that's where that's the main point we're focused on to evaluating our anchoring system. So you can see here, basically, all the lines are pretty close, specifically our solid line to the load cell and the jack. 120 tons is what we expected for failure for that. And then we were within 113, 116 tons. So about 3% error on the pure vertical test. The horizontal one, similar results. Again, we're focused on the dotted line, the vertical dotted line is where we define failure. And we anticipated about 75 tons, and it came in about 72 tons. So again, about 4% error, well under 5% error, which we were shooting for basically 5% under. We've since then updated our models. So basically, based off these results, we've gone back and updated models, and so we're better than these 3 and 4% failure criteria now. So then we also ran a scenario where the red line is kind of a theoretical, if we were to install a caisson of the exact same size without the helical piles, how it would perform under lateral loading. So basically our system versus a caisson of the same size, same weight, and we're basically 3 times more efficient. So the helical piles, those 9 extra helical piles, which are not cost or are very cost effective, increase the capacity by basically 3x. That's what I have. We can take questions at the end. Thank you.
Good morning, everybody, and thank you for coming to this session. My name is Spencer Hollowell. I am a senior research engineer at the University of Maine at the Advanced Structures and Composites Center in Orono, Maine. This talk today will be about the development of a taut synthetic mooring system for shallow water for a 15 megawatt floating offshore wind turbine. And this NowRDC and NYSERDA sponsored research is just closing out, so this may be the final time that I get to talk about this. And we have kind of exciting results that I can summarize for you today. So overall, our project objectives for this were to develop a 25% feed, and that's front-end engineering and design, for a nylon mooring system and anchors for a 15 megawatt floating offshore wind turbine, but for 56 meters of water depth. So for those of you that were in the one of the last sessions yesterday looking at some of the foundation technologies for fixed base, we saw some water depths maybe up to about 60 meters. 55, 60 meters of water depth is very shallow for floating offshore wind, and it poses several challenges. You can no longer use just plain catenary steel chains. It becomes incredibly expensive and costly, and staging things for floating wind in those depths doesn't become very cost effective. And so this project looked to use new synthetic mooring technology, which is proven at least for polyester in the oil and gas industry, and at least for nylon here, we have several demonstration projects in Europe that use nylon permanent mooring ropes to see whether we could push the limit of these shallow water depths. And make it viable for floating wind in these transitory areas. We then validated our design through numerical model test. At the University of Maine, we have a wind wave basin where we can test scale models of floating offshore wind turbines. Using those tests, we can ensure that the global performance of the mooring system and the floating offshore wind turbine model match what our numerical models that we used in design say. So that's a validation process, and that was validated through third-party review from National Renewable Energy Labs. The third kind of component of this was to confirm the rope properties that we used in our design through full-scale and sub-rope testing, witnessed and certified by ABS. That's a very important step because synthetic ropes have very nonlinear properties. The stiffness of the rope changes with the mean load and the load range that you're working with. And so capturing that appropriate behavior in the design and analysis phase is very important to make sure, again, that the global analysis that you're doing for the overall design makes sense from a realistic physical standpoint. The last step was to go through a certification process through ABS, through their approval in principle process. They basically review our entire design package up to the 25% feed and say, yes, this is a very reasonable design. For future detailed work, here's what you need to do to extend this to a real deployment offshore. All of those steps basically get us to a technology readiness level of 4. This research was used to kind of spin off in the University of Maine. We do pre-feed commercial work, and we already have completed 2 pre-feeds using a nylon semi-taut system based off of this research, which is, I think, a very successful deployment of the technology. And then we've also modeled our next research program through the California Energy Commission, basically modeling, using this research process as a model for deep water moorings, also using synthetic mooring ropes. This is our project team. We had a technical advisory team. Like I said before, NREL did a levelized cost of analysis as well as the validation of our numerical and basin models. ABS and DNV offered us review, and of course ABS is doing the approval in principle at the end of the project. We had a rope testing team, Stress Engineering Services, are experts in terms of synthetic rope testing and technology, and they helped write our test specifications, which ultimately were done at Houston Holloway, which has one of the facilities capable of actually breaking the mooring ropes of this size and scale. The design team included the University of Maine, who led up everything, as well as several partners to make sure that the design that we were coming up with was realistic and would actually work for a floating offshore wind installation. So that included Houston Offshore, which is now Kent. They provided us an installation procedure for our mooring system. Bryden Beckhart provided us with the initial rope properties, as well as the samples of the sub-ropes and the full-scale ropes that we tested to failure. Vryhoff, now Delmar Systems, provided us anchor designs, and of course, Triton provided us a helical pile design as well, so that we could see what the effect of different anchoring designs is on the cost of the synthetic system. So all of that being said, this is what the design of our system looks like conceptually. We have a relatively tight mooring radius. We wanted to push the limit of how small we could go for mooring radius here. So the radius is overall 300 meters from the center of the floater out to the anchoring points. Since the floater is very large for a 15 megawatt system, the radius from the edge of the hull out to the anchor point is only 242 meters. So we really pushed the envelope there as to how small we could go. The system is in between a taut and semi-taut system, so we have a length of anchor chain connected to the anchor, which is then connected to a nylon tether up to the fair lead chain. The nylon rope diameter was 220 millimeters in diameter, so it's quite large. That has a mean break strength of about 13,000 kilonewtons. So we're talking very large, very strong ropes. We included positive buoyancy within the construction of the rope. So for those of you familiar with some of these systems, you sometimes need to put buoyancy within the line to ensure that the synthetic ropes don't touch down on the seabed. That's a very important condition for the certification bodies to ensure that the integrity of the rope is maintained throughout its lifetime. You can achieve that in several ways. You can have a buoyancy module or can that's connected somewhere in the length of the mooring system. Bryden Beckhart offers a product where they actually integrate pieces of foam in the rope construction to provide that buoyancy. We opted for that system because we like the idea of having fewer things, fewer connections. We think that's a really resilient way to do mooring design. And the addition of the buoyant rope offers another advantage. And when we check the design case where one of the lines is failed, that line will now float up to the sea surface and be more easily recoverable when compared to a buoyancy can that may only be connected to the anchor chain. You may lose that rope and it could float around and potentially have a secondary entanglement on the rest of your wind farm. So we thought that that was a pretty slick way to cover both a seabed contact and a resiliency problem for a failed line case. The anchor chain here was sized to be 76 meters in length. We could have gone smaller there, except for the fact that for a reasonable installation, Kent gave us the really good advice that we should probably have enough anchor chain where a vessel that is handling the system can come and pick that chain back up off of the seafloor and do all of the ancillary connections that they need to do so that you can install the anchor, prelay the anchor chain, and then come out at a later time and have very easy connectability. So if you remember, our water depth here is 56 meters of water depth. That 76 meters allows you to get all the way up through the water column and have several meters of chain on the handling vessel to make those connections. So that becomes a lot more cost effective than trying to just shorten and spare change for the anchor chain there. The handling of the chain and the mooring system becomes a relatively large expense. Similarly, the fair lead chain is 30 meters of length so that we can ensure safe interaction with the floating hull when we're doing the actual hookup when the vessel brings the wind turbine out to the site. You want enough anchor chain there so that you can pay out during the connection. As I said before, the nylon rope has a mean break strength of about 13,000 kilonewtons. The anchor and fair lead chains need to be slightly larger because those components are fatigue driven, whereas the nylon rope is ultimate limit state driven. As part of this system, we need to come up with anchor designs that are reasonable, as well as have anchor designs that can have a reasonable amount of uplift capacity in some of the ultimate limit state design cases that we are encountered. So you can see in this table here, we have some of the maximum tensions on the anchors, and we have uplift angles in these cases anywhere between 6 and almost 10 degrees of uplift. And so, of course, the Triton anchor system has inherent uplift capacity because it has those vertical loads. And we've also pushed the Stevpers, the Vryhof drag embedment anchor, has uplift capacity as long as that uplift is temporary. So if you're uplifting that drag embedment anchor only for several seconds, which is the case in some of these ultimate limit state conditions, it can survive those cases. As long as the mean uplift angle remains relatively low or almost perfectly horizontal, ABS has approved the behavior of that type of drag embedment anchor. As I said before, we did a basin model test of our system here. The interesting thing that we implemented in this test, and for those of you who were here for my talk last year about this, we did an active mooring control system for this test to replicate the nonlinear properties of our mooring system. So basically, we have a linear actuator here in the bottom left, and we can program that to have basically any lookup table of behavior for a mooring system that you would want to implement. And that actuates the mooring system based on a load cell measurement connected to the floating hull. So the floating hull moves, it's not being controlled by the mooring system per se. The load cell reads what the tension in the mooring line needs to be, and the linear actuator changes its position to match what the stiffness is supposed to be at that given load level. So this was a unique and novel way to be able to allow us to be able to model those nonlinear systems. Because when you have the wind turbine scale model, in this case we use Froude scaling to get the 15 megawatt to actually fit into our wind wave basin, the material properties of the mooring lines that you can get off the shelf, whether they be monofilaments or very thin steel cables, the stiffness of those lines does not match what the material stiffness of a real nylon full-scale rope is. So you have these scaling issues when you do these basin model tests. Now that we have this linear actuator technology, that scaling issue becomes a little bit less important, and we can have a lookup table that exactly replicates what the behavior of the mooring system should be. The next step in one of the new tasks that I haven't presented on before are the results of our sub-rope as well as full-scale rope testing. So I've said multiple times now that the behavior of these ropes is nonlinear. This is what that nonlinearity looks like. You can see that the system starts out soft, which is a good thing. So you're not accumulating load in kind of everyday cases. As the system starts displacing, as the strain increases, the stiffness also increases. That's also a good thing because we're also offset limited. We have a dynamic cable connected to the floating turbine. So we don't want that thing floating off hundreds of meters, otherwise you're going to sever the dynamic cable. So the nice thing about nylon and even polyester ropes is we can change the construction and the lengths of those segments to fine-tune the design of our synthetic rope mooring system to match both the stiffness and the offset properties that we're required to meet for the other systems that we care about in our global design. You can see here I have three curves. We have the dashed blue line is the curve that we used in the design and analysis of our system. The red line is post-installation, so that would be after a vessel comes in, hooks up your system, does a pre-stretch operation, and then connects the various components. And then we have a worked-in rope stiffness line here. So that would be after, say, the first 1 year or so mean return period storm hits your system, that's what the stiffness of the rope is. Basically, all that's showing is the difference in the creep in the system from when you install it to the first year if you were to go out and then measure the stiffness of the rope again. And as you can see, the lines that we have, the red and the orange lines that we tested, match very well with the lines that we had for our design. The other thing here that I want to point out is the behavior there between post-installation and worked in. One thing that we've thought about conceptually is maybe not doing a pre-stretch task with a vessel because the loads that you have to pull the ropes are quite high to get those levels. And we are theorizing that maybe you allow several storms to pull on those ropes, get out the construction stretch, and then have your wind turbine work on something that's maybe a little bit less stiff and designed for that. That wasn't part of this research, but it's certainly something that we're going to be looking at for the California Energy Commission project, where we're extending the synthetic rope technology. So those were quasi-static stiffness tests. That's when you pull on the rope generally relatively slowly. The next thing was to confirm the dynamic stiffness of our rope. So as I said in the beginning of the presentation, we have different properties, stiffness properties of the rope, depending on what the mean load levels and the load ranges are for your rope. In this case, we did find a little bit of deviation from what we used in design to what we tested. The difficult thing is getting the low amplitude stiffnesses correct. In this design in particular, we have a lot of low amplitude action for a lot of the operational cases of the wind turbine. So we found in general we have about 25% error in the stiffness at these low load levels. And so what that means is at a more detailed design phase, we would go in and we would update our analysis and our load model to make sure that we're getting the appropriate stiffness levels at the load ranges that control the design. I will say a caveat here that these dots don't represent the entirety of the load ranges that we looked at for all of the design load cases. Several slides ago, I think I showed 4 or 5 of the load cases we checked for ultimate limit state design. And so you would see a scatter plot here that basically covers the entire graph. So there's a lot that goes on, and you have to make sure that you're using the appropriate stiffnesses, like I said before, to ensure that the global performance of the system matches what you have. So we propose here that you can update your parameters for those of you who are familiar with the quasi-static and dynamic stiffness analysis method. In the second column here, the 1.1, 0.475, that's what we used in design. We can use the updated sub-rope testing to go back and reevaluate our stiffness, dynamic stiffness with new constant and mean load amplitude parameters here, and hopefully get a better view of what realistically the behavior of the system would be. So this is where I wish I had a video, because we also did full rope testing, both cyclic and brake tests. The nice thing about having video for the cyclic tests is you can see how long these tests take. So we tested over 10,000 cycles, which for fatigue testing doesn't sound like a lot, but the amount of load and stroke that the system has to pull on these ropes, you're talking about strain levels up to 15, 20, over 25% elongation, means that the hydraulic system is very taxed. So this is an incredibly strong rope, incredibly stiff. It takes a lot of energy. So our 10,000 plus cycles took almost 3 full days for our cyclic test. And it was done in Houston in September, and for those of you familiar with the weather down there, it was over 100 degrees. They had to shut down the hydraulic system several times during this test. So we're constrained in the capacity of the different testing facilities that can actually test ropes this size, and even bigger is what we're going to be going to for bigger floaters and deeper water. And even with the facilities that do exist, there are constraints in what can actually be done, because we have old systems that were designed to test offshore oil and gas products, and now we're looking at bigger and different products that have a lot more elongation, and that's a difficult thing to do for the hydraulic systems. So the idea here is we did 1 full cyclic test of a rope. We didn't take that to failure. Of course, 10,000 cycles, if it failed then we'd be in trouble. But what we did here is we cycled it at 10,000 cycles, and then we tested that 1 rope to failure to ensure that it matches the brake strength of the 2 remaining samples that we had. Again, I wish we had an ability to do a video here, but this is a setup of the brake test. The reason a video is really impressive is, first, the video starts with an air raid siren. And the reason there's an air raid siren is because you don't want anybody anywhere near this when it goes off. The amount of load and elongation, which means energy in the system, is actually quite spectacular here at failure. So it becomes very dangerous, and of course in a video, when it lets go, it sounds like a gunshot. It is like an explosion of energy. Pieces of rope go flying everywhere, water spraying everywhere because the rope is fully saturated. It is a really fun and impressive thing to see. So this is what the rope looks like as it's failing. So we can slow down. You can do it on an iPhone now. We did it on an iPhone. You can slow down the frame rate really slow, and you can see the ropes actually retracting. So the load-bearing fibers inside of the polyester overlay start retracting back out to the splices where they connect to the eyes of the testing rig. And that happens over a factor of a couple of milliseconds. So we tested these ropes to over almost 13,000 kips and 40 inches of displacement stroke in the system. So if you do that energy calculation, it's equivalent to over a kilogram of TNT exploding in this test rig. So that's why the air raid siren goes off. And it is really cool as you can see this failure progressing along the length of the rope. The other interesting thing is all 3 ropes failed in different ways. This rope in particular was the rope that was cyclically tested. That one failed within the gauge length of the rope. You could see the load-bearing fibers retract out to the splices. The other 2 ropes were combination failures, and actually the failure initiated at the splices. And so that's another thing that becomes very difficult with synthetic ropes is when you do the splices, which are the portions of the rope that are connected at the ends, you have to hand lay that. And so from what we've learned, that is both an art and a science. And it's a very important way that the loads get shared across the fibers to ensure that when you make that slice, it has the capacity of the full rope. So here's what the 3 rope tests look like here. The biggest takeaway, I think, is in the middle column here, we reached 95, 94, and 93% of our target MBL. That's the target MBL of the gauge length of the rope unspliced. So you can see that the introduction of the splices, especially for the first 2 rope samples here that failed near the splice, saw reduction in capacity because of how that was done. The 3rd rope that we cyclically tested 10,000 times had a very, very small reduction in capacity. Now, we don't know if that's just variability in the rope construction. If you test multiple samples, of course, you're going to have variability in capacity. Or it could have seen a little bit of cyclic degradation in the 10,000 cycles that we had. More work would certainly need to be done to do so, but these fatigue tests and full-scale tests are time costly as well as monetary costly. So that makes things quite difficult. So to wrap things up, we wanted to look at an economic cost of what these systems would look like compared to a typical catenary system that might be costed for shallow water. Of course, we're not going to go to an incredibly heavy system in shallow water for a catenary chain, but we wanted a cost basis for comparison so that we can understand whether or not this is going to be reasonable to install and if there are any cost savings. So in terms of CapEx, we saw that compared to a catenary system, which of course probably isn't the best system for a really shallow water installation, we saw just over 3.8% reduction in CapEx. And when you look at the entire array of, in this case, we looked at a 40 turbine array, we saw a total reduction of 2.7% in the LCOE of the entire system. So mooring systems, it varies what the LCOE component of a mooring system would be for a floating offshore wind farm. But in this case, going to a semi-taut system that uses synthetic ropes and nylon in particular can give almost a 3% reduction of cost for 40 wind turbines. So to conclude, we, I think, pretty successfully designed a shallow water synthetic mooring system for a New York Bight specific location. We looked to do 2 different anchor sizes, which were both approved by ABS to be used for this type of concept. And we saw a pretty significant reduction in levelized cost of energy for a 40 turbine system. We developed a 1/70th scale model test and a novel way of doing active mooring control for nonlinear mooring design. And we looked at sub and full scale rope tests to confirm the design assumptions that we used for our global performance analysis. So looking ahead to the future, I mentioned we're going to be looking to do some work for deep water systems in California. There's a question about what the low tension fatigue performance is for synthetic ropes, especially nylon. That question whether or not those 10,000 cycles degraded the rope is a pretty big one outstanding in both the literature and industry. And so we're looking to hopefully do some rope tests that involve those low tension cycles. And we're also looking to see if we can come up with a test procedure that doesn't require full-scale rope tests, because like I said, they're costly, expensive, time-consuming, and if you're going to have to do multiple ropes per wind farm, we're going to exceed the capacity of the testing facilities in this country. So we need ways to test ropes faster and better. And with that, I look forward to your questions. Thank you.
Good morning. My name is Bill Fang. I work for GE Global Research. The project is joined with Virginia Tech, with the Professor Zhou, Lei Zhou, as the PI. When we started the project, he was a professor in Virginia Tech. Now, recently, he moved to University of Michigan. As you can see, we have quite an array of graduate students working with us. Some of them we recruit to the GE. I think Duncan is in my group, Ryan is in gas turbine, and we also have a PhD. Jim is in Michigan, and Java is the postdoc. So it's quite a team. Well, I think the question we try to answer is, if we move a fixed base wind turbine to a floating system, what is the problem? There's 2 issues jump out immediately. One is the load become bigger, right? This chart shows a load comparison between a floating system versus a fixed base. And especially if you look at a place like a towel-based bending moment, it depends on different style. Currently, there are so many different style of floating system. I think the most popular one, I should say, is the we call semi-submersible. Those are typically very wide, pretty shallow, usually have 3 big cylinders halfway submerged into the water. The advantage of this system is they are really easy to assemble. Basically, you can assemble this system onshore, and then have a boat drag this out to the side and anchor right there. So that's the attractiveness of this style. The problem is this style of platform is very flat and very big. So they vibrate quite a bit. So besides the more load you have to deal with, the second issue is the vibration. If you have a fixed wind turbine putting on a floater, what you will observe is, for example, in the pitching system, that's the nodding of the system. Sometimes system amplifier, so you will pitch more and more, the whole system just shaking. A way to deal with it, obviously, is you can feather or you can pitch the blade away from the optimal angle to stabilize the whole system. But by doing so, you sacrifice the production of the energy. So it's very critical to have some sort of mechanical damper to stabilize the system, either by control. You can have a smart control system, or have a damping system, vibration absorber, sort of, to deal with it. So just quickly, a very common method to putting a damping system in a big structure like this, we're talking about thousands of tons of steel, is they call tube mass damper. Example here, this is the Taipei 101 in Taiwan, one of the largest tube mass damper system implement on the top of the building, mainly for earthquake, this system. So the idea is if you have a really big mass M0, you attach to a relatively small mass M with the stiffness and damper, or viscous damper. When big mass M0 start to vibrate, the idea is you want to transfer all the kinetic energy to the small mass. So the big mass remains stable, small mass will vibrate like a crazy. And that energy essentially go to this C, the viscous damping system. So that's where the energy channel to it. For wing system, because we are dealing with a very large mass, very large system, to make this system effective, the small mass need to be typically like a 5% to 10% of a big mass. You cannot have like a really tiny mass attached to a huge gigantic mass and expect this to be effective. So it is okay for some systems, but for us, even 5% of mass is lots of metal we need to add to the system. So we need to find a smart way to deal with it. One of the system, I would say, improvement over the traditional dual mass damper is we use so-called inerter system. So inerter is a system proportional to the relative motion between the small mass and big mass. In our case, we want to add a generator or energy harvester system between the small mass and big mass. So the idea is, instead of channel the kinetic energy to viscous damper, which basically turn into heat and dissipate away by heat, we want to channel this energy to something more useful. In this case, you can think of channel that energy to generate additional mass. There are two benefits of doing that. Obviously, you gain additional energy by channeling this amount It's something like a 5% of your production energy, additional energy. The second thing is this will provide amplification effect of your damping. So sort of when a big system start to, the small mass vibrate a lot, as I mentioned, when resonance occurs. So you hold a generator against the small mass vibration. So essentially you are holding the system from vibrating a lot. It's like you drive your car downhill and you put on the low gear, an engine is spinning faster, holding the car from, you don't have to apply brake all the time. So this is the same effect. You sort of can apply a flywheel, if you would, on the end of the system, which will holding the vibration from just going crazy. So this is the mean of amplify the damping effect and also provide additional energy. So that's the main principle of that. Theoretically, you can see, without any control, obviously the thing will vibrate quite a bit. With the TMD, the two-mass damper, the blue line, it will damp out the system. But if you add this TID system, we call it, it's going to further damp out the vibration, as well as generating about 5% additional energy. So basically, you channel this vibration energy into the generator. So our target is we want to stabilize the platform by 20 to 40%. In addition, ideally, we want to harvest additional 10% of electricity. This is the goal. I think right now we are looking at somewhere between 5 to 10%. That has to be optimized. So sort of you have a dual target. You want to minimize the vibration. You also want to maximize the additional energy. So in a sense, you cannot satisfy both. So you can play with the game, maybe find a sweet spot somewhere to have both reasonably good. And we also want the system to be retrofittable to most of the existing system. So what you saw here, this is a standard Enreal 5 megawatt kind of design with big cans. Those cans are about 12 meters in diameter, about 20 meters long, each of them. So we want to use the empty space inside the can to put a mechanical system like that on the right. I will explain a little bit more how this works. Some result from the analytical study. We mainly target at pitch angle, which is the system nodding back and forth. Heave is the system moving up and down. So pitch is the most critical because in the wing, the thrust load is the largest. And when the thrust load being amplified, right now the only way is you cut back your production. So basically you pitch the blade to reduce the load, to stabilize the whole system. So that is the most critical motion we try to damp out. There's two lines on this chart. There's a red line and blue line. The red line is the TMD, the traditional two-mass damper, and the TID is with this additional inerter in the system. What we want to demonstrate is if you replace, if you draw a horizontal line, so basically you can have the same percentage of vibration reduction by moving, if you jump from the red line to the blue line, you can use about 1% less mass to have the same effect, same reduction. And this effect is more with the heave motion. Actually, you can get about 2% reduction in the mass. So previously, for example, you need a 5% of mass to damp out your bigger mass. Now you can use 4%. In the heave case, you can even use 3%. So we are achieving about anywhere from 20 to 40% almost reduction in the mass. A more realistic system is with the wave and the wing, and in some cases, wave and the wing come with different angles. So this is the study showing in the time domain, we call low condition 1. So this is the 8 meters per second as average wind speed with 10% turbulence intensity. Wave here is 2 meters, wave period is 10 seconds. So what we want to show is what is this system capable of. You can design basically the system to target at different frequency. You can target at your most frequent wave period, or you can target it as natural frequency of the water dynamic in the pitch direction, which has a slight different frequency. In real case, the wave is highly irregular. So you will have all kinds of frequency components. So it is become a big optimization issue. How do you design? In our case, we have 3 different damper, and we want to damp out basically all motions possible. This picture shows the frequency domain. It's the same simulation as the previous slide, which showed the time domain. And what this demonstrates is this system is capable of damp out a peak, which in this case is the natural water frequency. So if you let system do itself, nodding in the pitch direction, that would be the frequency you saw. It is actually a pretty low frequency, but the system is capable of damping out lots of vibration, the zoom-in version of that, with all angles. So 0 degree means the wind and the wave come at the same angle. 30 degree is wind and wave with the 30 degree angle apart. More result, we're also looking at the higher wave case. In this case, LC2 involve 16 meters per second wave, wind speed, sorry. And the table on the right is show the reduction of the vibration. And basically across the board, with the different angles, this system works, first of all. It reduces lots of, the TTFA response is tau top forward after. That's the nodding motion of the tau top. Across the board, you will see a huge reduction. And if you compare the traditional TMD and TMDI, which is the inerter works better. But inerter has second benefit, as I mentioned. It will generate additional energy. There's some mechanical device we need to design, because as the system moves linearly, the small mass move inside the cylinder, move up and down. It drives a generator. The best way the generator works is rotate in the single direction. So if you have a generator rotating this direction and then reverse, the generator won't work half of the time. So we have to design we call mechanical motion rectifier. It's basically a small gearbox. This gearbox turning up and down motion into single rotating degree of freedom. So it's always rotate at either clockwise or counterclockwise. It never reverse. The way we do it in this case is we have 2 one-way clutch, one-way bearing system. So these bearings, you can only rotate one way, and if you want to reverse, it will stuck. So you have 2 of these bearings on the both side of, in the middle, it's a traditional racket pinning design. So there's a linear motion, can go both backwards and forward. But when you have 2 of these one-way clutch on both sides of racket pinion, you turn this 2-way rotate up and down motion into one-way directional rotation. This shows a picture on the bottom. The blue curve is, let's say, a sine wave input to the system. So your pinion is running forward and after. After this system, it turned into all positive. The negative disappeared with this system. In addition, because generator has its own inverter, this system is actually nonlinear. This blue line is like, if you don't have an inertial system, you will have up and down this sine wave into a double peak, all positive system. In reality, because the generator, when the input is 0, the generator still have inverter, it's still spinning. So in reality, you will get this red wave. You never goes down to 0 in the system because of that. It's sort of, I put a bicycle guy here. It's you pedal downhill, so sometimes you cannot pedal because the bicycle go down by itself quicker than you can pedal. So you feel like, your pedal like empty almost. That's the same thing because the generator at that point has its own inertia moving down. So you never really get down to 0 in the system. It becomes a nonlinear system. It actually make analytical work a little tricky. But yeah, it's a fun system to work with. Because of that one-way clutch, now the mechanical system, theoretically, you have a period that system disengaged from the generator. So we have 2 different cases with the engaged system and disengaged system. You can optimize with the system. The chart, the frequency domain chart on the right show 3 different systems, basically. Is the pure Tillman's damper. The second one is TMD, but without this one-way clutch. So basically, it's a flywheel system. The TMD can go both ways. And the final system is more realistic. If you want to put a generator, the generator only spin one direction. You need, we call MMR. So now you can, like I said, you can tune the system to one way or the other. As you can see, the TMDI, the dual direction system, in terms of pure vibration reduction, it works better. However, the TMDI with the MMR is better because it has additional energy generated. So, 2 systems you can tune one way or the other. And, we try to hit both basically with this setup. Another thing we are doing currently is we want to optimize the energy production with the additional generator. We want the system to be engaged as much as possible. Even you have a period that it was disengaged, you rely on the generator inverter in that case. With a little mathematical work, we start with a simple system we call swept sine exciting. So it's a standard way to design a vibration system. Basically, you have input with a bunch of sine wave with different frequency. So it's all sine wave, but they come with a different frequency. You want system to handle all different frequency of sine wave. So we optimize this system. Currently, we can have 350 kilowatt at the maximum output with this is additional energy, and system engage about 84% all the time with this setup. Obviously, this is the real situation is more complex than a pure sine wave. So I think we are working. Let me just jump to the last slide. Yeah, I think we are working on the full scale system currently, try to optimize for the entire system. Last one. All right, so this is the last slide. Just to summarize, I think the inverter system seems to be promising. It works better than the pure TMD. It also provides additional energy generation. Now, 5% seems to be a small number, but it could be critical in case, for example, if you have a storm case, your system is down. You have to shut down your turbine. this additional vibration-induced energy can be very useful to help you running the pitch, running the yaw system even. Currently, in the turbine, we have a battery system, but only lasts a couple of minutes. So this additional 5% energy is extremely useful for many things: maintenance, emergency system, extreme load reduction. It could be very beneficial in many circumstances. I think currently we are working with the MMR system, try to design a more realistic. So basically, this is a one-way clutch system to turn up and down motion into one rotating direction. This will drive a linear generator, but we have to optimize the system. Again, currently there's two different targets: vibration versus additional energy. And we may have to find a sweet spot to work on both. This is it. Thank you.
And so I'll invite the panelists up. So thanks for the questions that have come in on Slido so far. Starting with Triton, can you elaborate some on the installation procedures and what vessel? Can you elaborate on the installation procedures?
Yes. Okay. Yeah, so we, like I said, we have the subsea installation tool. It's basically, a custom remotely operated vehicle. So the installation tool is attached to the anchor on the vessel. It then lowers through the water column together, lands on the seafloor together, and then we have individual drive motors. The individual drive motors screw in the helical piles, and then the helical piles pull in the caisson into the ground. Ultimately, the installation tool hydraulically unlatches from the anchor and then comes back to the vessel to then get reloaded with the next anchor. Different installation processes are possible, like two tools, one reloading, one installing, different type of vessels, just depending on what's necessary.
Is there roughly, what would be the installation cost versus the material cost?
Material cost is definitely the significant cost because of the high quantities. So there's obviously a quantity changeover where, like in a demonstration unit, the installation cost is the majority of the cost. When you have 300, 400 plus anchors, then the manufacturing cost is the significant driver for us. We install about 3 a day, depending on the sizes, potentially more per anchors per day.
Okay, and then we got a few questions about nylon rope. It's known that nylon can lose some of the mechanical properties in the marine environment, such as creep problems. So just kind of explain, why did you choose nylon?
Yeah, so for the shallow water environment that we were looking in, we needed compliance. And there's several types of synthetic ropes. Each of them has their own, pros and cons. Nylon is usually the least stiff of the synthetic ropes that are available commercially. And so the shallow water environment, you attract a lot of dynamic loads from the waves. If you were to resist those loads with just, say, a heavy chain or a long taut rope, the stiffness kind of gets you. And so the loads amplify on your hull, on your connections, and also importantly, the anchors as well. So by putting this nylon, essentially tether in, the material stiffness is quite low, but it is nonlinear. So you start off with a very low load level, and then that load level increases as the offset of your platform increases. So it's kind of that sweet spot. You can get similar behavior with load reduction devices. The purpose of this research was to look at synthetic moorings, and of course I think we've heard in previous symposia about the load reduction devices that you could use to achieve that as well.
And for GE, so the two-mass inerter damper, how would it compare to an active ballast system? What are the advantages of doing the damper?
Yeah, I think an active beta system, I assume you have to mechanically control it. This is a passive system. We kind of try to eliminate additional mechanism in the offshore environment just for reliability. And traditionally, two-mass damper is a very reliable system. As you saw, all the big buildings have employed similar device. The problem is, as I mentioned, the mass becomes so enormous in the system. It becomes economically unfeasible if you just do a pure mass damper system. So this is an attempt to basically amplify your damping effect while generate some additional electricity. So I think when we started, we keep reliability in mind because that's the most important thing in the offshore environment. So all the components selected is readily available, commercial available off-the-shelf kind of a product. In general, they are fairly reliable in this kind of environment. So I think that's the main reason.
And for Triton, can you compare the noise level difference, if you're familiar with like monopile fixed bottom installation versus an anchor installation noise?
Yeah, we were definitely significantly less than a hammer solution or a driven pile solution. We don't have exact measurements yet. We have a program coming up to hopefully measure the exact differences, but we would basically be the similar noise level that a suction bucket would have. A suction bucket would have an ROV down there, operating thrusters, motors, things like that. Pumps, we have the exact same type of pumps, thrusters, motors and stuff like that. So no exact numbers, but similar to a suction bucket level of noise is what our anchor would have, significantly less than a driven pile solution.
Thanks. And then for Maine, so there's a comment that a major country supplying nylon rope is Russia. Can you comment on the supply chain for nylon rope, and then, or maybe compared to like whatever the default maybe chain solution would be?
Yeah, that hurt us in this project. Our test campaign for the full-scale rope tests was delayed pretty significantly. So the supply currently globally is difficult, especially for nylon. Compared to say chain, for the chain sizes that we're looking at, and for the scale, if we're trying to hit the Earthshot challenge, we don't have the chain capacity available globally either. There just is not enough chain for hundreds of wind turbines being installed for floating installations. I will say the nice thing about synthetic ropes is there are synthetic rope manufacturers domestically. They may not specialize in nylon right now, but the construction of the ropes maintains pretty similarly across the different synthetic fibers. You're developing yarns and sub-ropes, and you're weaving those sub-ropes into full-scale ropes. So there's no reason that a domestic supply chain couldn't be developed for nylon systems. It's just not there yet.
So what was the length of chain in your system compared to if it was an all-chain, like catenary system?
So for the preliminary catenary system we sized just for LCOE purposes, what we did is we took the designing load case for the nylon system, which turned out to be DLC 6.1, and then we sized a chain so that the mean break strength matched the demand loads for that. And that was almost a 700-meter long system, so a significantly larger increase in the amount of chain. Now, I keep saying many times that you would not propose that system, I think, realistically, but it was just a very quick look at what it might look like and what the costs would be for that heavy length of chain.
And then for the TMDI system, do you need to have the damper in all 3 columns of the semi-submersible, or would it be possible to have it in just 2?
Right now, we are targeting at all 3, and we're also targeting at all 3 with the different parameters. So you can optimize. So basically, you have more knob to play with in the system. And in this design, there's a different motions. So you can argue there's 6-degree freedom. You all want to damp it out. For us, as I mentioned, most important is the pitch and the heave. So we try to make all 3 work. We start with assuming all 3 has a different parameters, but right now we are opening up to have different parameters for all 3. I think that works better, especially for irregular wave cases.
And do you know if there's much noise generated by the TMD system that might be transferred into the water?
It's encapsulated, inside these columns, so we don't believe there's lots of noise. We haven't looked at, how much noise is going to be generated due to the system. I think the main noise is going to be the gear system and the rack pinion in the middle. You saw the pictures. But I think with the proper insulation, especially they are inside the column, so I think it shouldn't be tolerable.
And so for the nylon rope mooring, did you consider connecting the nylon directly to the hull and eliminating the fairlead chain?
Yeah, so we did consider that, but one of the downsides to nylon is it degrades in UV. So when you have the rope exposed above the sea surface, you get severely degraded properties, and it actually happens pretty quickly. And so one question is, how deep do you put the nylon to be safe? In shallow water, we probably can't avoid some UV degradation. So there's an operations and maintenance plan that you have to go in and inspect whether or not the fibers are being degraded. And I will say that there is a protective kind of wrapping of fibers, a sheath that goes around the load-bearing ropes. Typically, that's polyester, I believe, for the nylon rope construction. But even that will degrade in UV, and so you would have to have a pretty accelerated O&M plan if you were to put it connected directly to the hull.
Okay, and then I guess for Triton, what's next for advancing your anchor?
Yeah, so like I mentioned, we have to finish the last stage of ABS qualification. So that is us basically doing stage 4 again, but offshore. So site survey, design of anchor, manufacturing of anchor, installation, and then load test. The only difference on the load test is we won't be able to measure as precisely. It'll just be a pull test to kind of design load, make sure the anchor doesn't pull out. But we basically won't pull test them to failure just because we can't measure the amount of small load or measurement changes that happens underwater like that. And then we're advancing the design for several different soil types, more complex soils. So to date, it's been mainly like all clay or all sand seabeds. So we're getting more data that's more mix of both. And so we're optimizing the design for various maybe site-specific designs.
And so for the nylon mooring, so knowing that it doesn't have the track record as polyester, what next is needed for certifying nylon?
More rope tests, and specific to the load ranges that we care about for floating offshore wind. Nylon is often used in lifting mechanisms, and so it's used kind of as a shock absorber for those systems. And there are test data for those types of systems, but they don't use the load ranges that we do. We're very dynamic. We would like to bring the mean load as low as possible so that we can keep pretensions low. But there's a dearth of test data available for the performance of the ropes at those load ranges. So low tension cycle fatigue is a big question. And then I think long-term durability is another question. And there are deployments in Europe that are currently using permanent moorings for floating offshore wind turbines with nylon. That's great because we'll be able to test those post-mortem to see what the reserve capacity is and whether there's been degradation. And then future test data on that, the low cycle fatigue will let us know how far we can push the envelope for permanent nylon moorings and how long they can possibly last.
And so one more for the two-mass inverter damper. You mentioned so it's creating 5% additional electricity. Could it be used for like a black start scenario?
Yeah, exactly. I think we are thinking, additional couple percentage is critical. A couple of things, right? Emergency case, I mentioned sometimes your emergency case come when you lost the grid, and usually, something got stuck. And currently, backup system for the yaw system for the pitch only lasts a couple of minutes with the battery. So this, this system is independent of your grid. Basically, it's driven by the vibration of the system. So you can argue, in a stormy case, you get more energy out of this little generator. It could be used also for maintenance. Sometimes you have to shut down your turbine to do the maintenance for the safety of your personnel. So I think there's multiple usefulness for even 5% of additional energy available to you.
And for Maine, why did you look at such a shallow site condition?
That's kind of transitory where fixed bottom becomes really expensive. Floating is also expensive in terms of moorings for that location. But we wanted to push the envelope in terms of what we could do for the technology. And we could conceive of some sites where a fixed bottom foundation may not work just because of the geotechnical conditions. So you could decouple the system from being fixed to the bottom, put the turbine onto a floating hull, and then you just have to figure out how to maintain the station keeping with anchors and moorings.
And for Triton, can you describe how the spacing of the helical piles is determined?
Ooh, that's a complex one. Lots. I mean, basically, we've basically have classified the spacing requirements and the effects that the helical piles have in a tight clustered group, anywhere between like 9 anchors upwards of 50 plus anchors, anywhere from like 2 times the diameter of the plates to 5 times the diameter of the plates. So lots of testing, lots of analysis to determine, I guess, different effects at different sizes and spacings. There's no right or wrong spacing that we go for. I guess that we determine the optimal spacing, and the optimum is basically the lowest cost anchor. So we have a optimized anchor design software, and we plug in mooring loads, we plug in geotech conditions, and it outputs basically thousands of anchor options, and then we usually select the cheapest one, or maybe there's some variability in installation size and stuff like that.
Okay, and we're heading into a break now, and I think the next floating session will be in the same room after the break. So thank you for the great questions, and thank you, panelists.